Deep Learning Part 3: Loss and Gradient Descent. We can run a network forward and get a prediction. But fresh from random weights, that prediction is nonsense. To fix it, we first need to measure exactly how wrong it is, and then take the first step to make it right. Here is the situation precisely. The network makes a prediction, the data holds the true answer. Between them, a gap. Training has exactly one job: shrink that gap across every example in the dataset by adjusting the parameters. But a gap is a vague thing. First, we must turn it into a single hard number. That number is the loss. A loss function takes the prediction and the target and returns a measure of how bad the prediction is. High loss means very wrong, zero loss means perfect. It is always a single number, no matter how large the network. And the entire enterprise of learning is the search for parameters that make this one number small. For predicting a quantity, the natural choice is squared error. Take the difference between the prediction and the target, then square it. Squaring does two things: it makes the error positive either way. And it punishes large mistakes far more harshly than small ones. Predict 0.37 when the truth is 1, the squared error is 0.40. For classification, we use a different loss, cross-entropy. It looks only at the probability, the network assigned to the correct class. The loss is the negative logarithm of that probability. Give the right answer a probability of 0.37, and the loss is 0.99. As the probability approaches 1, the loss falls to 0. As it approaches 0, the loss explodes. The logarithm punishes confident mistakes mercilessly. One example is never enough. The total loss is the average over the whole dataset. L of theta equals 1 over n times the sum of the per example losses. And here is the crucial shift: this single number is a function of every parameter in the network. Change a weight and this number changes. Minimizing it is the whole game. Picture that function as a landscape. The ground beneath you is the space of all parameters, the height at each point is the loss. Mountains where the network is badly wrong, valleys where it is right. Training is a walk across this landscape. And there is only one rule for the walk: always head downhill. But how do you walk downhill when you cannot see the whole map? You feel the slope beneath your feet. The derivative of the loss with respect to a weight is exactly that local slope. A positive slope means the loss rises as you increase the weight. A negative slope means it falls. The slope at your feet points the way. This gives the update rule, gradient descent. Move each parameter a small step in the direction opposite the slope. The weight becomes the weight minus eta times the derivative. Eta is the learning rate, the size of the step. Downhill to the right, step right; uphill to the right, step left, always toward lower loss. Watch it on the simplest case. A single weight, a bowl-shaped loss with its minimum at 3. Start at 0, the slope there is steeply negative, so we step to the right. Again and again. Notice the steps shrink as the slope flattens near the bottom. And the weight settles exactly at 3, the minimum found without ever seeing the whole curve. Everything hinges on the learning rate. Set it too small and training crawls. The weights barely move and progress takes forever. Set it too large and you overshoot the valley. The steps bounce from wall to wall or fly apart entirely. Set it just right and you glide smoothly to the bottom. Choosing it well is half the craft of training. Real networks have many parameters, so the landscape has many dimensions. With just two, we can still draw it, contour rings around a minimum. At each step, we read the slope and move downhill. The path curves inward toward the center. And the loss in the corner readout falls step by step toward zero. In many dimensions, the slope becomes a vector, the gradient. One partial derivative for every single parameter. Each one answers a local question. If I nudge this one weight, how does the loss respond? Collect all those answers into one vector and it points straight uphill. So we step exactly opposite, steepest descent. The real landscape is not a single clean bowl. It is rugged and vast, many valleys. Gradient descent only ever goes downhill, so it can settle in a local minimum that is not the global best. There are also saddle points, flat in one direction, falling in another. And yet, remarkably, in very high dimensions, most of these traps turn out to be shallow, good enough to work. Computing the loss over the entire dataset for every single step is far too slow. Millions of examples just to move 1 inch downhill. So we cheat cleverly. Estimate the gradient from a small, random batch of examples. This is stochastic gradient descent. Each step is cheap, and we take thousands upon thousands of them. That batch estimate is noisy. So the path down the landscape jitters and wanders instead of gliding. But that noise is a feature, not a bug. The random kicks can bump the parameters out of shallow traps a perfectly smooth descent would get stuck in. Noisy and better for it. We can do better than plain, independent steps. Momentum. Keep a running average of past gradients, a velocity, and move along it. In a long, narrow valley, the side-to-side wobbles cancel out, and the consistent downhill direction builds up speed. The ball rolls instead of stepping, faster and steadier. Modern training adds one more refinement. Give every parameter its own adaptive learning rate. Parameters with large, noisy gradients take smaller steps. Those with small, steady gradients take larger ones. This is the idea behind optimizers like Atom. Momentum and per-parameter scaling combined, the default for most networks today. And the learning rate need not be fixed throughout. Start it large to cover ground quickly early on. Then shrink it over time to settle gently into the minimum without overshooting. This is a learning rate schedule. Big strides at the start, careful, tiny steps at the very end. A warning and a comfort together. For a simple bowl, a convex loss gradient descent is guaranteed to find the one global minimum. But a deep network's loss is not convex, rugged and full of valleys. No such guarantee exists. And yet in practice it works astonishingly well. The theory is still catching up to the fact. Put it all together and this is what training looks like. The loss plotted against the number of steps. It starts high, drops quickly, then flattens as the network approaches the bottom of the landscape. One full pass through the data is called an epoch. We run many. That falling curve is learning made visible. But we have quietly assumed something enormous. Every step needed the gradient, the slope of the loss with respect to every weight. For our tiny network, we could imagine computing it by hand. For a network with millions or billions of weights, that is unthinkable. So how do we actually get the gradient? This is the single most important algorithm in all of deep learning. It computes the gradient of the loss with respect to every weight in the network, all of them in one efficient sweep. Without it, none of this would be possible. It is how every network, from a single neuron to the largest models ever built, is actually trained. So part 3 in one line. The loss measures wrongness, and gradient descent walks the parameters downhill to reduce it. We have the compass, we know which way is down. What we still need is a way to read that compass cheaply for millions of weights at once. Next, part 4, backpropagation.